The title of this lesson is Functions. By the end of this lesson, you will be able to identify which relations are functions, which relations are not functions, and also you should be able to identify the domain and the range of different functions. But before we are able to do that, we need to talk about what a function is. A function is a relation in which every element in the domain, or x, maps to exactly one element in the range, or y. Another way that we can say it is that every input has exactly one output. So for example, when we consider x to be our input, so whenever we look at the x value, then we look to y to be our output, there should only be one y value associated with every x value. I'm going to go through a little demonstration of what a function is. It's kind of a casual demonstration that I like to use. It asks you to think about a Coke machine. And I believe I talked about Coke machines in the mapping diagrams. So the input of a Coke machine is typically the button that you press after you put your money in, and the output is the drink that comes out of the Coke machine after you've pressed the button. So let's pretend that our Coke machine has button A, button B, button C, and button D. A function is just like a working Coke machine. So for example, let's say we get the possible drinks: Coke, Diet Coke, Sprite, and Dr. Pepper. And if you press button A, you get a Coke. Button B, you get a Diet Coke. Button C, you get a Sprite. And button D, you get a Dr. Pepper. When you go to that Coke machine and you press a button, you know exactly what drink you're going to get. That is a function, because the input has exactly one output paired with it. So let's pretend that maybe we mess with the wires a little bit. And the wiring of the Coke machine looks like this. Do you notice anything wrong with this Coke machine in the way that it's wired? You should, because if you press button B, you will either get a Diet Coke or a Dr. Pepper. This is exactly what a non-function is, because the input B has two different outputs B. You don't know exactly what you're going to get, so this is a non-function. Let's try rewiring. I want you to ask yourself, if I were to press each button or each input, do I know exactly what the output is? So think about it. Does this Coke machine model a function or not? It does. Even though the different inputs have the same output, we know exactly what the output is going to be for each button. If you press A, you know that it's going to be a Coke. If you press B, you know it's going to be a Coke. C, it's going to be a Coke, and D, it's going to be a Coke. This is a function. So I know this is a casual example. I won't exactly test you on Coke machines, but I want you to be able to apply this model to more mathematical examples. This diagram that I showed you is a diagram of a mapping, and in the previous lesson we looked at a few different mappings. There's a one-to-one mapping, a one-to-many mapping, a many-to-one mapping. Which of these model a function and which ones do not model a function? Take a second and see if you can identify. Does a one-to-one mapping model a function, yes or no? If you answered yes, then congratulations. A one-to-one mapping is a function because every domain value has exactly one range value. Now let's look at one-to-many. Is a one-to-many mapping a function, yes or no? No, this is not a function. In this particular case, the domain value 2 has two different range values associated with it, and the domain value 4 has two different range values associated with it. So this is not a function. Move on to many-to-one. Does this represent a function, yes or no? Well, if you look at all of the domain values and then follow the mappings, do you know exactly what the output or the range value is going to be? You should. This is a function. Even though all of the inputs had the same output, there was only one output associated with each input. So yes, a many-to-one mapping is a function. Sometimes you'll look at relations like this, where it's just a set of ordered pairs. So here's a problem. For each relation, identify the domain and the range. Then determine if the relation represents a function or not. Okay, so for the first one, I'm going to make a set D for domain. And it's really easy to identify the domain for these types of problems. All you have to do is look at each x value. So my x values here are 1, 5, 3, -1, and 0. So I'm going to put those in a set of brackets. And there's my set that represents the domain. For the range, those are our y values. My y values are 7, 15, 11, 3, and 5. The second part of the problem says to identify if this relation is a function or not. So you ask yourself, do any of my x values get paired with more than one y value? Well, in this case, no, that's not the case. Every single x value has exactly one y value. So this is a function. Let's look at the second example. Identify the domain and the range. So I'm going to say D for domain, and I'm going to list all of my x values. I have 4, -2. There's another -2 listed here, so I don't have to write it twice. 0 and 2. Range values are -8, 4, 7, 3, and 1. Okay, look at all the x values or all the domain values. Do any of the domain values repeat? Yes or no? Well, in this case, yes. -2 is paired with both 4 and 7, so that's a problem. Therefore, this is not a function. That wasn't the pen, but it's written in really bold writing. Sorry about that. Okay, you try. Press pause, and I want you to answer the following 3 questions. Identify the domain and range for each, and determine if they're a function, yes or no. When you press play, I'll put the answers up. Okay, so for problem 1, the domain is 3, 5, 1, 5, and 3. The range is 6, 2, 6, 0, and 4. And actually, I rewrote 6. I didn't need to, so I'm just going to erase it and make this a little shorter. Okay, the domain value 5 is paired with both 2 and 0, so this is not a function. Second one, we have -7, 0, 3, 2, and 3. Range is 8, 1, 7, -9, and then 1 pops in there again. Is it a function, yes or no? Well, the domain value 3 is paired with both 7 and 1, so this is not a function. And then the last one, domain, would be 3, 5, 1, 4, and then there's a second 3, but I don't need to write it again. The range is 4. Well, it's 4, 4, 4, 4, and 4. And then look at all of my domain values. I do have a repetition of 3, but really it's the same point. So every domain value is paired with only one range value. This is a function. Okay, sometimes we look at relations in a graph form. There are some relations that have so many points in them, they're infinite sets of points, that we can't possibly list out all of their ordered pairs. So we graph them. This graph right here looks like a straight line. My arrowheads on either end indicate that the line continues in those direction, in infinite direction. So our question is, identify the domain and the range, and then determine if the relation is a function. And you know, actually, I'm going to see if it's a function first. It's really easy. When you look at all of your x values, there should not be any x value with more than one y value. So we do what's called the vertical line test. If I were to draw a vertical line at any point on this graph, and it were to cross more than once, then it would not be a function. Well, in this case, a vertical line could pass through any point on the graph and only cross once. So this is a function. Identifying the domain and the range is a little trickier. So let's start with the domain. The domain is the set of all x values. So I'm going to compare my graph to the x-axis. And when I do, if I were to say compress this graph on top of the x-axis like this, it would touch every single x value on that x-axis. So in this case, our domain is really easy. Any real number could be a potential domain value. So what I'm going to do is I'm going to say domain equals, and then that's the symbol for the real number set. So when I say this, this means that the domain can be any real number. Another way you could express this is you could use it, you could say it in words. You could say D equals all real numbers. That would work too. Okay, now let's identify the R. Notice I don't have a double bar because I want to use the actual letter R to represent range. To find the range, that's your set of y values. So I'm going to compare the graph to the y-axis. If I were to compress this graph along the y-axis, and on this way too, it would touch every single y value. All of these y values are potential outputs in this graph. So again, this range could be any real numbers. Or if you prefer not to use the symbol, you could just write it out. All real numbers, that's fine too. Let's try another one. Okay, first of all, is this graph a function, yes or no? So to answer that question, we have to do the vertical line test. And so when I look at it, I see that it would actually fail the vertical line test. If I draw a vertical line here, do you see how it crosses more than once? Well, that means that this x value, -2, has two different y values paired with it, 3 and -3. So this is not a function. All right, now let's list the domain. Compare the graph to the x-axis to find the domain. If I were to compress that graph along the x-axis, I would see that the lowest possible x value is -4, and then when I keep compressing this graph on the x-axis, there really is no highest value. So I'm going to write an inequality to describe all of the possible x values. And we'll use interval notation. So I'll say x such that, okay, so since -4 was our lowest possible x value, I'm going to say that x is greater than or equal to -4. So when anyone reads this interval notation, they would understand that the domain for this graph can be any real number that is greater than or equal to -4. Let's look at the range. The range is the set of y values. So compare the graph to the y-axis. If you were to compress the graph on the y-axis, that would touch every single y value. It would continue infinitely in the positive direction and infinitely in the negative direction. So what I'm going to do is I'm going to say that range can be any real number or the set of real numbers. Okay, I want you to try. This graph, I want you to identify the domain and the range, and I want you to determine if it is or is not a function. Press pause and try and work it on your own. Okay, so first of all, it's really easy to determine if something is a function or not if you give it in a graph. This particular graph isn't drawn very pretty, but it continues in this pattern on and on and on. So this is a function. Okay, the domain. Imagine smushing that graph along the x-axis. If it continues on infinitely towards the left and to the right, then every single x value is represented on here. So my domain is any possible real number. Now let's compare it to the y-axis to find the range. if I were to kind of crush this graph along the y-axis, it's only touching values from -3 all the way up to +5. There are no y values graphed anywhere up here or anywhere down here. So my range has what we call a lower bound and an upper bound. So I need to write an inequality using interval notation. So I'll say range equals. This time, since we're talking about range, which is y values, I'll say y such that. And then to write my inequality, the way I like to do it is I will write out the lowest possible value, which is -3, and I'll write the highest possible value, which is +5. Then I'll place a y in between them, because y is between -3 and 5. And then I like to fill in with my inequality signs and then close out my brackets. So this interval means that y is anything from -3 to +5. Let's try that again. Here's a graph. Press pause. I want you to determine if it's a function, and I want you to determine its domain and range. Okay, so this is very obviously not a function. It fails the vertical line test. The domain, which is the set of all x values. When I look at the x-axis and I compare it to my graph, my lowest possible x value is -4. And then all of these x values are included in the domain. My highest possible value, x value, is +4. So I need to write an inequality to describe all of the x values from -4 to +4. So I'll open a bracket and say x such that -4 is my lowest value, +4 is my highest. I'll put an x in between and fill in the inequalities. Oh, oops, went backwards, sorry. And then I'll close my bracket. Okay, for the range, remember, compare to the y-axis. So if I were to compress this graph on the y-axis mentally, it would touch all of these y values from -4 to +4. So my range is very similar. But remember, we're not talking about x values anymore. We're talking about y values. So we'll say that y can be any real number from -4 to +4. I have one more example for you. This will be kind of a lead-in as to why functions are related to some real-life situations, or what kind of real-life situations can be shown with a function. Look at these two graphs. Which one makes sense to you and which one doesn't? Which one do you think is a function? So both of these graph the trip to Grandma's house for Thanksgiving, and let's say you're measuring every hour how many miles your family has traveled in the car. So on the left-hand graph, at 0 hours, you had traveled 0 miles. At 1 hour, you had traveled 50 miles. At 2 hours, 100, and so on. Look at the second one. It's also saying that this is my trip to Grandma's over time. Do any of the time recordings make or not make sense to you, I guess is what it should be asking. You're probably looking at these 2 points. Can you be in 2 different places at the same time? Yes or no? No. Time travel hasn't been invented yet. There is no way that we can physically be 150 miles from our distance and 75 miles from our distance at the same time. So the left-hand graph is a function. The right-hand graph is not a function. Any kind of motion or data collection that we're doing in real time or in real life is usually a function. Functions just make sense to us. That's why we can model our trip to Grandma's using a function like this. A couple of vocabulary terms that you need to remember. All of the domain or the x values we call the independent variable. That's what we use when we speak in more real life terms. The range values or the y values are called the dependent variable. The distance you have traveled depends on how long you've been traveling. If we were to write the domain and the range for our left-hand graph, the trip to Grandma's, let's think of what the lowest possible value is. Is this an infinite situation? Could domain be any real number? No, it couldn't, because we can't have negative hours. So I'm going to say that my domain is anything greater than or equal to 0. The range for this situation, again, distance traveled, well, 0 miles is our lowest possible distance traveled, so I'm going to say that y is greater than or equal to 0. All right, so that concludes the lesson for today. I hope you enjoyed it. If you weren't sure of anything or you need to rework any of the problems, be sure to rewatch the video. Come with your notes to next class and we'll discuss any questions.